Right, let's jump straight in. Have you ever looked at a tiny, seemingly insignificant object and wondered just how much secret potential it's hiding? Well, today on The Explainer, we are going on a bit of a scientific detective story. We're going to calculate the sheer, unadulterated power hidden in something you could literally hold in the palm of your hand, a single handful of uranium. By tapping into the magic of physics, we're going to uncover a scale of energy that is, frankly, completely mind-blowing. So, the central question we're tackling today is actually pretty simple. How much energy is really hidden inside just one handful of uranium? Sounds straightforward enough, right? But to actually get to the bottom of it, we have to take a journey from the absolute tiniest building blocks of the universe all the way up to the massive power grids that keep our modern world humming. We're taking things from the micro straight to the macro. So, let's start small, like really, really small. Section 1. The subatomic spark, a tiny unit of energy. Our detective story kicks off way down at the microscopic level. We're talking about the exact moment a single atom splits. When that happens, it releases exactly 200 mega-electron volts, or 200 MeV for short. Now, in the world of particle physics, this is a super specific and incredibly important unit of energy. It represents the exact energy released during the fission, the splitting apart, of just one single uranium-235 isotope. Think of it as a single subatomic spark. But it kind of begs the question, how big is that spark, really?
To really wrap our heads around this spark, we can convert that 200 MeV into joules, which is just your standard scientific unit for energy. It comes out to approximately 3.204 times 10 to the negative 11th power joules. Just to put that into perspective for a second, that negative 11 means you've got a 0, a decimal point, 10 more zeros, and only then do you get to the actual numbers. So on its own, this subatomic spark is infinitesimally tiny. You wouldn't even notice it happened. But what happens if we gather up a whole bunch of these atoms? Section 2. The scale of a mole. 6.022 times 10 to the 23rd pieces.
Okay, so the crucial piece of the puzzle here is understanding the concept of a mole. And please, don't let the terrifying scientific math scare you off. A mole is really just a scientific constant. It equals exactly 6.022 times 10 to the 23rd power pieces of something. Honestly, the easiest way to think about it is like a scientific dozen. Just like a dozen always means 12, a mole always means this massive number, a 6 with 23 zeros after it. In physics, we use this scientific dozen to count atoms in a tangible amount of material. And as luck would have it, 1 mole of uranium-235 is roughly what you could comfortably hold in a single handful. Section 3. Kilowatt hours. Everyday energy. Scales.
Now, to bring all this abstract physics down to Earth and into our everyday lives, we need a standard unit. Enter the watt-hour. A watt-hour, or WH, is simply a unit of energy that represents 1 watt of power sustained for exactly 1 hour. But you're probably way more familiar with its larger cousin, the kilowatt-hour, or kWh. When you rip open your utility bill at the end of the month, you're being charged by the kilowatt-hour. It's the totally standard, everyday metric for the energy we consume in our homes.
Just to ground this in reality, 1 single kilowatt-hour can actually power some very relatable stuff. It's enough to brew roughly 100 cups of coffee. It can run a large flat-screen TV for 10 hours straight, or it can power your washing machine through 1 complete heavy load of laundry. So keep that 1 kilowatt-hour in your mind as our baseline as we move forward.
Section 4. The grand conversion. Energy calculation.
I absolutely love this part. Let's walk through this mathematical journey together and treat these numbers like plot twists in our mystery. Step 1. We take the energy of our single atom, that incredibly tiny 3.204 times 10 to the negative 11th joules. Step 2, we multiply it by 1 mole, our scientific dozen, which is that huge 6.022 times 10 to the 23rd atoms. Step 3, we get our total joules. When you actually multiply those together, the math spits out a staggering result, approximately 1.93 times 10 to the 13th power joules. Just like that, our tiny invisible spark has turned into a roaring, gigantic fire of mathematical energy.
But let's be totally honest here. Joules are kind of alien to most of us. To really grasp what we're looking at, we need to convert this back into our relatable household metric. So, to convert joules into kilowatt hours, we take our massive 1.93 times 10 to the 13th joules and divide it by 3.6 times 10 to the 6th power. That's just the standard conversion factor that scientists and engineers use all the time.
And when we punch that final division step into the calculator, we get 5,360,000 kilowatt hours. I'm just going to pause for a second to let that number really sink in. Over 5.3 million kilowatt hours of energy are physically hidden inside just one single mole, one handful of uranium-235. It's almost unbelievable.
Section 5. Powering the world. Visualize the scale. When you visually compare these numbers side by side, the difference is just staggering. An average home's annual energy use sits right around 10,000 kilowatt hours. Okay, makes sense. A small city block's network uses about 500,000 kilowatt hours. But that single mole of uranium-235 absolutely dwarfs them both at over 5.3 million kilowatt hours. To truly appreciate the massive scale of nuclear power, you really have to see it stacked up against the electrical networks we interact with every single day. Let's break this down even further, because these specific examples are just mind-blowing. Think about an electric vehicle. A full charge takes about 80 kilowatt hours. With the power contained in our single handful of uranium, you could fully charge that car roughly 67,000 times. Or look at the average U.S. home. At 10,000 kilowatt hours a year, that single mole could power a family's home for 536 years. Think about that. Even a massive, energy-hungry factory, which easily chews through 1 million kilowatt hours a month, could run off this for over 5 entire months. All of that from one handful of atoms.
And that brings us to our final thought for today's explainer, the incredible, almost magical density of nuclear physics. By systematically breaking down the math today, we've revealed something that is truly extraordinary. We went from a subatomic spark that you can't even see or feel, to a colossal force capable of powering literally centuries of human life. It really leaves you wondering, doesn't it? If this much energy is locked inside just one handful of uranium, what other incredible, unimaginable power is hidden right under our noses, deep inside the atoms of the world all around us?